In this lecture, we're going to be working with radical equations. Usually we think of radicals as things like square roots or cube roots. Of course, a square root is the same as x to the 1/2. A cube root is the same as x to the 1/3. And then let's say we had something like x to the 3/4. How would we write this in radical notation? Well, we've looked at these before, and remember, 3 is the power. It's the numerator, and the denominator is 4, which is the root. So this is the 4th root then of x cubed. So we're going to be talking about these equations, and of course when we say equation there's an equal sign involved. And we're trying to find the real solutions. So we're not working with complex numbers here, we're trying to find the real solutions of quadratic equations. One thing that I want you to watch out here in this assignment is extraneous roots. Extraneous roots are solutions that you get, you haven't made any mistakes, the solution that you get at the end of a problem that when you plug them in they don't actually work. So we must check all solutions every time. And of course we're going to be using our graphing calculators as well to help us check solutions. So we'll see how these work here. But every single one of these problems has to be checked for extraneous roots. This is a really important point. So let's go ahead and get started by looking at some examples. Let's look at the square root of 15 minus 2x equals x. So first of all, the square root sign goes over the 15 minus 2x, everything on the left-hand side, and the right-hand side is just equals x. Now what I'd like to do to start is I would like to graph this. Now when we graph this, everything has to be set equal to 0. So I have my 15 minus 2x, and then I have to subtract the x and get it set equal to 0. Now notice this minus x is not underneath the radical, it's separate. So let's go ahead and grab our graphing calculator and have a look at what this is. So to graph we hit y equal, clear anything that's in there. Now second x squared on my calculator is my square root. And underneath your square you'll have 15 minus 2x. Then you need to make sure that you scoot out from underneath the radical to put in your minus x. So this is what your expression looks like right here. Now let's go ahead and graph this. We may have to change our viewing window just because we might not be able to see where the entire graph is. Okay, so this looks pretty good. I think that I want to change the viewing window just a little bit because there could be another solution somewhere else. I'm definitely seeing a solution right here at 3 or around 3, but I want to double check and make sure. So I'm going to change my viewing window. And y max, boy, that goes up to 50. I don't think we need 50 there. Let's go up to 10, and then it's my x values where the roots show up. So I want to know where this crosses the x-axis. So I'm going to go negative 20 to 20. And again, you have to check because there might be another solution. You just might not see it because of your viewing window. Okay, yeah, it definitely looks like it's going right around 3 or maybe exactly 3. Let's go ahead and paste this into our lecture so we can see where that solution comes from. And then let's look at the table, because remember we can look at the table in MyMathLab to see if that is crossing at an integer value or not. So let's go ahead and, or not MyMathLab, sorry, on your calculator. So let's go ahead and go to second table. And we think that that root is somewhere right around 3. Notice all my y values are positive, but they're getting smaller and smaller. Oh, there's our solution. Now notice right here where I have y equals 0, x is 3. That's my solution. So that's telling me the solution to this equation is 3. So I have a pretty good idea what's going on here with my solution already. Now we'll check it by hand. But again, I would always encourage you to graph these to see what they look like because that will show you how many solutions that you have. You do have to be careful though because sometimes when you're looking at these windows, I might be cutting off the solution we can't see. So here's my solution, or my root, or my 0. They all mean the same thing. And this is telling me I have a solution here as well. So when I get done, I think my solution should be x equals 3. But let's see what happens when we do this by hand. So by hand, I have the square root of 15 minus 2x equal x. Now I don't want to move the x across when I'm doing this by hand. That's only for graphing. This is a square root. So this is the same as the 1/2 power. To undo a square root, we want to square both sides. Okay, so square both sides. Now if this was a 4th root, we'd take both sides to the 4th power. If it was a cube root, we would take both sides to the 3rd power. Now over here, when I square the square root, I just get my radicand back. So I have 15 minus 2x equals x squared. Now this is the equation I want to solve. The extraneous root comes into play right here when we square both sides. Because when I square a positive number, I get a positive value back. And when I square a negative number, I get a positive value back. So what ends up happening is one of those numbers that I'm squaring, either the positive or negative, has the potential of actually not solving one of these equations. Now to solve, I want to get this set equal to 0. So if I do that, I'll have x squared, and then I'm going to add the 2x across, subtract the 15 across, equals 0. Now if I wanted to graph this just like I did in solving quadratic equations, I could do that and see where it crosses to find my roots. This one in particular factors very nicely. I could also use a quadratic formula, completing the square. This one I'm going to solve by factoring. But again, you could graph this. You could use quadratic formula, completing the square, but this one does factor nicely. So if I factor this into plus 5 and minus 3, notice I have 5x minus 3x gives me my 2x. 5 times a negative 3 is a negative 15. And then what I'll do next is I'll use my zero factor property. X plus 5 equals 0, or x minus 3 equals 0. Zero factor property is very handy solving. And in this case, I'd subtract 5 from both sides. And here, I get x equal negative 5. That's strange, because we didn't see that in our solutions. And over here, when I add 3 to both sides, canceling, I get x equal 3. So what we have here are potential solutions. So these are potential solutions. Remember, rule 1 on here was must check for extraneous roots. That means one of these may or may not be a solution, or maybe even both of them. So I have to check both numbers. Well, we already know from graphing, we already know that 3 is my solution and negative 5 is an extraneous root. But let's see how we do this by hand, because we want to be able to do things with our calculator and by hand. So we go back to our original and we would check both of these. X equal negative 5. So this would be the square root of 15 minus 2x equal x. And I'm trying to figure out if this is true. So everywhere that there's an x or a blank, I'm going to go ahead and plug in a negative 5. Well, we know right away if I take the square root of something, I can't get a negative back. For instance, the square root of 25 is 5. The square root of 36 is 6. So if we keep simplifying, I get 15 plus negative 2 times negative 5 is 10. Again, I'm checking. 15 plus 2 is 25. The square root of 25, we're looking for the positive root. If there was a negative sign out front, I could get a negative sign out of this, but I'm only looking at the positive root. So 5 does not equal negative 5. Therefore, x equal negative 5 is an extraneous root and not a solution. Okay, so you can throw that one out. Again, our graph that we did up above verifies this, but this is how we check it by hand. So we do the same thing over here, except this time we're checking to see if 3 is a solution. So we plug 3 in everywhere there's an x. Then over here I'd have 15 minus 6, checking to see if this is a true statement. 15 minus 6 is 9, and the square root of 9 does equal 3. So 3 equals 3, therefore x equal 3 is a solution. And we saw that from the graph, and we see this when working the problem by hand as well. So these are the types of problems that we're going to be looking at. And one of the things we need to keep in mind, our original problem only had one square root sign, and what you want to do is isolate the square root, and once the square root is isolated, square both sides. So let's continue to look at a few more problems. And remember, one of the things we always need to keep in mind is we always must check for extraneous roots. So this one, let's go ahead and start with the square root of x plus 8 equals x minus 4. The square root is already isolated, and because it's already isolated, I don't need to worry about trying to get it isolated, and the first step I can take here is just going ahead and squaring both sides. Whatever you do to one side, you do to the other. So when you square the square root, you just get the radicand back, and I get x plus 8 equals x minus 4 quantity squared. Now remember, x minus 4 quantity squared is not x squared minus 16. I can't take the 2 and distribute it. This is equal to x minus 4 times x minus 4. And then I'd either FOIL this out or use the box method on this. If I FOIL this out or use the box method, I get x squared minus 4x minus 4x plus 16. First outside, insides, and lasts. Now my goal here is to get this set equal to 0. So we should kind of jump back up on here. First of all, we square both sides to begin with. Our next step here was to expand the right, and we did this by FOILing. And then my next step will be set equal to 0. Okay, so I'm going to move the x and move the 8 across, and I'll have x squared minus 4x minus 4x plus 16 minus x minus 8 equals 0. So I just move this by subtracting x and subtracting 8, and then we will go ahead and combine like terms. Now when I combine like terms, constants go with constants, x's with x's, x squareds with x squareds. You can see we have a negative 4, minus 4 is a negative 8. Negative 8 minus 1 more is negative 9x. And then of course we have 16 minus 8 is going to be plus 8. Okay, so this is going to be set equal to 0. Now we want to factor this. Or I could use a quadratic formula. We just need to basically solve this. So we want to factor, use a quadratic formula, something to solve this. You know, and I forgot to graph this one right away. When we get done, we'll graph it, and then we'll verify our solutions. But I should have probably graphed it right away so I had an idea of what I was shooting for my solutions. This does factor nicely into x minus 8, x minus 1. So now I'll use the zero factor property. Now with this zero factor property, either one or both of these factors must be equal to 0. So I have x minus 8 equals 0, or x minus 1 equals 0. Okay, the one on the left, I would add 8 to both sides. These would cancel, and I'm left with x equal 8. Then I would add 1 to both sides over here on the right, plus 1, plus 1. I always got to keep that balance. Whatever you do to one side, you do to the other. And I have x equal 1. Now these are possible solutions. Possible solutions. So we have to take these possible or potential solutions and check them for extraneous roots. Okay, so how do we check for extraneous roots? Well, what we do is I take each one, in this case x equal 8, and I plug it back into the original. So my original was x plus 8 equals x minus 4. So everywhere there's an x, I'm going to plug in an 8. And again, this is just following from my original. So here I have 8 plus 8, that's the square root of 16. And again, I don't know if this is true, if these are equal or not. 8 minus 4 is 4, the square root of 16 is 4, 4 equals 4. This checks. Therefore, x equal 8 is a solution. So this one, I have one solution so far, and I need to check x equal 1 next. So again, back in my original, everywhere that there is an x, I will plug in an 8. So I'll plug in, or sorry, I plug in a 1 because I'm checking x equal 1 here. So 1 plus 8 is 9, so here I have the square root of 9, and 1 minus 4 is negative 3. But I'm looking at the positive root because there's no negative sign out front here. So the square root of 9 is 3. 3 does not equal negative 3. Therefore, x equal 1 is not a solution. It is one of our extraneous roots. And I didn't do anything wrong. It's not a wrong answer. It's just called an extraneous solution to this problem. And they occur when you end up squaring both sides. So the one thing I forgot to do here was to graph this. So let's go ahead and continue on with this problem. We better note down here that here's my solution. Let's continue on with this problem and let's graph it and check our solution that way. Okay, so same problem. Just continuing on, we're going to graph this. Now remember, when you graph, you have to have it set equal to 0. So this was my original. So what I can actually plug in to my calculator, I would need to subtract the x, minus x, and add the 4 and set it equal to 0. Now notice the minus x and the plus 4 do not go under the radical sign. So let's go ahead and graph this. Pop open your calculator, go to the y equal button, and remember, if you already have something in there, you want to make sure you clear it out. And here I'll have the square root of x plus 8. Make sure you get out from underneath that radical sign before you go minus x plus 4 and graph this. Now we might have to change our viewing window. Let's see what pops up here. Okay, now what I see here is not a guarantee of one solution, because it could have popped up somewhere else. You know, it might have curved up and hit over here outside the range of my graph. But we've already done all the handwork here, so I'm pretty confident that this one solution that is showing matches with what I think my solutions are over here. Now from here we thought x equal 8 is a solution. Now if we look at this graph, this kind of looks like it verifies that, but let's go ahead and go back to our table. Remember, you go second table, and there it is. There's that x equal 8 clear at the bottom. Y value is 0. That is our solution. Now a couple of interesting things. Notice my y value switched from positive to negative, and in between is my solution. So anytime you see that switch from positive to negative, you know that there's a solution or a root in between. So let's go ahead and pop this in as well. And both of these verify the same thing, one solution. I don't have two solutions, I only have the one solution that I verified. And this definitely looks, if I count over, x equal 8 as well. This is my solution. And another name for a solution is root or 0 of the function. And 0 just means, where do I cross the x-axis? Where is my y value equal to 0? So I think this verifies the same thing, x equal 8. And this also shows that my other solution, x equal 1, definitely is not a solution here. It's extraneous, because if you plug in a 1, I'm clear up here on the y-axis in the positive direction. So graphing first is helpful. I should have graphed this one first, but we can always graph it in the end as well to check our answers. The next problem that we're going to look at is a little different in that it has radicals on both sides. Now these are long problems. You kind of have to keep track of where you're at in the problem. And sometimes you'll get to a solution and you've done so much work you think, well, I've done enough work, I must be done. But remember, you have to check for extraneous solutions. The last one I forgot to graph right away, so this one, let's go ahead and graph this right away. So if we graph this, everything on the left stays on the left. And we have to subtract everything from the right over or add it over depending. So I can set it equal to 0. So this is what I want to graph. Now there's no guarantee that my viewing window is going to be correct. So always keep that in mind. Sometimes when you look at these you think, well, it's not showing up in my graph so there's no solution. Well, it might be just outside of your graph and you're just not seeing it. So we have square root of x plus 27. Now this one's a little different because I have two radical signs, and we'll show you how to deal with that when we get to this in terms of the handwork. Then we have the square root Okay, I think we have the calculator freezing up here. So I will exit out here real quick and get back in. Okay, I have my calculator up and running again, so we've entered the equation square root of x plus 27 minus the square root of x minus 6, and then notice when we subtract the 3 across, it's not under the radical. Let's go ahead and graph this and have a look. Now the way that this looks right now, it appears that there's no solutions at all. It doesn't ever cross, it looks like it gets close. And then let's go ahead and look at our table as well. What are all these errors? Well, these errors come into play because when I take a -2 and I plug it in up here, -2 minus 6 is the square root of a -8, which is not a real number. So all of these errors are occurring because I cannot get a real number solution. So I have all these positive values, and if you notice, these positive values are getting closer and closer to 0, so that's an indication that I might be crossing the x-axis, because remember, when they switch from positive to negative, that means that I've crossed the x-axis. A switch has occurred. So these are still positive, getting smaller. Whoops, there's our solution right there, 22, 0. Now our table won't always have this. It'll only have it if we have an integer solution. So let's go ahead and copy this table and put it into our notes. So 22, 0, that tells me I have one solution so far. There might be another one. Maybe I need to keep searching. But it looks like for now I just have the one solution. Now with the graph, the graph's really not showing what's happening here because the scale is hard to see. So let's look at that graph one more time. If you look at this really closely, I can't really tell where it's crossing because I don't think this goes out to 22, first of all. And second of all, because my y scale is so large, it kind of compresses this and doesn't show how it crosses. So one thing we could do is we could take this window and we could switch it. My x min value, I could go to 0 because I know my graph doesn't even occur on the left. And my x max, I know I'm going to have to go past 22, so I'm going to go to 30. Y min, I'm going to really compress this graph a lot. I'm going to go from -2 to +2, because what happens then is it really stretches out where it crosses, and it might make it easier for me to tell where it crosses. Yeah, see now here I can tell. Before it was just skimming along here, but when you change that y scale and kind of spread that out, I can really see clearly that it's crossing. Now it could be crossing in another spot. Maybe it's way over here at 400 or something. I don't know. I'd have to change all of my settings to try and find that other root. So that's why we like to use handwork and our graphing work to help try and find those solutions. But for now, it looks like we're safe to say that 22 is one of my solutions, and if I count it over from here, 1, 2, 3, etc., I would get x equal 22 as my solution. So I think x equal 22 is my solution. But there could be another one out there. Now how is this going to change on how we solve this by hand, because it has two radical signs? So our strategy here is to isolate the radical and then square both sides. So one radical I can isolate. It doesn't matter which one. It could be the root x plus 27. It could be the root x minus 6. What I want to do is isolate a radical. So we could add the root x minus 6 across. Whoops, x minus 6. And again, whatever you do to one side, you do to the other. And what we see here then is on the left, this cancels, and I have indeed isolated that radical. Now I'm still going to square both sides. The right-hand side is going to get a little ugly when we square both sides. And of course, whatever you do to one side, you do to the other. And I have to square both sides. And on the right-hand side, it's going to be easy to make a mistake and just square the radical, but I need to square 3 plus the radical. So I have to FOIL out the right-hand side. On the left-hand side, when I square square root, I'm just left with the radicand back. Now here, when I square both sides, I'm going to write it out because I don't want to make any mistakes. And then I'm going to go ahead and FOIL it. So I'll expand the right or FOIL, however you want to think about that. Now remember, we can't just square the 3 in the radical. I have to FOIL it out. So my first would be 3 times 3 is 9. My outside would be 3 times the radical, x minus 6. Insides would be 3 times the radical, x minus 6. And my lasts would be the square root of x minus 6 times the square root of x minus 6. Now our hope is here that this will simplify, and you can see that some things will simplify, but we're getting into the case here when I square both sides that I end up with a radical on the right-hand side now, and I was trying to get rid of one. But the thing you want to think about here is that you got rid of the one on the left. So again, these are long problems. Now on the right-hand side, I have 9 plus, I have 2 of these. 3 radical is 6 radical. And then here I have root x minus 6 times root x minus 6, which is just x minus 6. So we're going to simplify. So I have 9 minus 6 is 3. 3 plus x plus 6 root x minus 6. Now I want to isolate the radical on the left. Okay, so what we want to do then is we'll subtract the 3 and subtract the x. And we end up with x minus x is 0. 27 minus 3 is 24. And on the right, these cancel. I'm left with 6 square roots of x minus 6. Now before I square both sides, I could divide through by 6 because 24 is evenly divisible by 6, so that could be one option here as well. Now if it's not evenly divisible, you could probably just leave it there, leave the 6 on the right and deal with it later. 24 divided by 6 is 4. And now I want to square both sides. And again, that will get rid of the radical on the right. So these are long problems. You can't give up on them. Whatever you do to one side, you do to the other. 4 squared is 16. 16 is equal to x minus 6. Again, when you square the square root on the right, you get the radicand back. And to finish this, we would add 6 to both sides. And I get 16 plus 6 is 22 equals x. This is a potential solution. And remember, we must check this for extraneous roots. Now we already know from our graph that it's good. It's a good solution, but let's go ahead and check this by hand anyway, just in case we get in a pickle sometime and we can't grab our calculator to check. How would we do this by hand? So let's go ahead and check x equal 22. So the way that this would work is I'd have my radical, and everywhere that there was an x, I would go ahead and plug in my value of 22. And I want to check and see if this is equal to 3. So 22 would go wherever my x was. Again, this is just my original equation. 22 plus 27 is 49, so I have the square root of 49. 22 minus 6 is 16, and I want to know, does this equal 3? Square root of 49 is 7. Square root of 16 is 4. 7 minus 4 is indeed 3, so this checks. Therefore, x equal 22 is the solution. And again, we saw that from our original graph as well. But you need to do these problems by hand as well, because we're going to run into some problems sometimes when your solution might be a decimal or a square root sign or something, and your calculator's not going to give you that number, so you have to be careful with that. Let's go ahead and work another one of these problems with the radicals on both sides, because they are pretty tricky. So let's look at another one. Square root of 2x plus 3, square root of x minus 2 equal 2. So I want to graph this right away. And we already know now when we graph something, it has to be set equal to 0. So everything on the left stays. And I subtract that 2 across. So let's go ahead and graph this. Y equal, and we clear out what we have there. So we have square root of 2x plus 3. Make sure you're out from underneath that radical sign. On some of your calculators, you'll just need to close parentheses, plus the square root of x minus 2. And again, we're going to subtract that 2 across, but that minus 2 cannot be under this radical sign, so be careful there. Let's go ahead and hit graph. It's kind of an interesting little graph. Let's go ahead and take a big look at this. Let's hit our zoom and go to zoom standard or zoom square, either one. I'm not sure which one is better. I think I better go to zoom standard. I want to see a little bit on the left. I'm not going to be able to do much here because both of these functions are only defined. This radical is only defined from 2 to infinity, and this one is only from -3/2 to infinity. So the domain for this function is the most restrictive, which would be 2 to infinity. So there's nothing going on over here, but if you weren't very good at trying to come up with that domain restriction, you would probably want to go back and look at zoom standard and have a look. Now it looks to me right here that this graph moves from here and keeps moving out. It could come down though, but right now it looks like there's no solution. It does not look like there is any solution here, but you'd have to check to be sure. It's not a guarantee. Just because you look at a bit of a graph and it doesn't cross the x-axis is no guarantee that there's no solution. It's just basically saying that in the viewing window that you're looking at, there's no solution. So if you change the viewing window, you might get more of a graph. So for here it looks like no solution. Now if we look at our table, let's see if that sheds any light on this. It shows that it's thinking. Let's see if it's stuck again. Second table. So again, we're looking at the table here. If you notice, our numbers are getting larger and larger in the positive direction. We need our numbers to be getting toward negative values. So they could be going up and then eventually start coming down. But as we kind of page through this, it really doesn't look like I have any solution either. But again, to be sure, you'd have to check every single number possible, which is a lot of numbers to check. So you can't really go this option. This is not a guarantee of no solution. This is just an indication of no solution. You'd have to do the handwork first to be sure. And again, our numbers are getting smaller. We might think that they're heading towards 0 and crossing the x-axis. But if you notice right here, as I do get toward that 0, I hit error. And that basically means all of the graph doesn't even show up over here in this error region. It's undefined there. So it kind of looks like no solution is the correct response here. And it's not no solution because of my errors here. It's no solution because it doesn't look like it crosses the x-axis. So that's kind of the indication, but again, the graph is not a guarantee. So the graph indicates no solution, but we must check by hand. Because again, it could be that this graph comes out in this direction and eventually crosses down here, and maybe it's just not in my viewing window. So but we must check. So let's go ahead and get started. What we want to do first, of course, is the same as our last one. We want to isolate the radical. So we would go ahead and subtract root x minus 2 from both sides. These cancel, and I'm left with the square root of 2x plus 3 equals 2 minus the square root of x minus 2. Next we would square both sides to get rid of the radical on the left. So I'm going to move down here. So we have 2x plus 3 equals, now remember, I have to FOIL this out. I just don't take the 2 and distribute it. I actually have to FOIL this out. First outside, insides, and lasts. So I have 2x plus 3 equals, first 2 times 2 is 4, outsides minus 2 root x minus 2, insides same thing, and then my lasts, I have a negative times a negative, which is a positive, x minus 2 root x minus 2. Okay, so simplifying further, I have 2 of these minus 2 roots, so that would give me a minus 4 root. And then root x minus 2 is a plus x minus 2. Combine some like terms on the right, and I have 4 minus 2 is 2, so I have 2 plus x minus 4 root x minus 2. I want this set equal to 0, so I'd subtract the 2 and the x from both sides. And here I have 2x minus x is x, 3 minus 2 is 1, and then over here I'm left with negative 4 root x minus 2. Now, if I wanted to divide through by negative 4, I could, or I can leave it as is. The last one I divided through, this one I won't, just to show you the difference. But I have to square both sides. So here I'll have x plus 1 times x plus 1. Now this square will distribute to the negative 4 to give me a 16. The square will distribute to the root, which will give me x minus 2. On the left hand side, I FOIL this out and I have x squared plus x plus 1 equals 16x minus 32. So I subtract 16x and add 32 because I want to get this set equal to 0. And I have x squared. X plus x is 2x. 2x minus 16x is a minus 14x. 1 plus 32 is 33. Okay, so let's go ahead and regroup here for a second and figure out how we're going to solve this quadratic equation. When we're solving this quadratic equation, the first thing I notice is 33 times 1 is 33. That doesn't get us to a 14. 11 times 3 is 33. 11 and 3, that could combine to a negative 14 as well. Let's see if we can make this work in factoring. So we'd have an x and an x. You can also use the quadratic formula on this as well. Let's do a minus 11 and a minus 3. So my outside would be a minus 3x, my inside would be a minus 11x, which gives me a minus 14x. And a negative 11 times a negative 3 is a positive 33. Okay, so this does factor. Now we'll use that zero factor property. X minus 11 equals 0. X minus 3 equals 0. On the left hand side here we'd add 11 to both sides and I have x equal 11. Here I'd add 3 to both sides and I have x equal 3. These are not guaranteed solutions. These are potential solutions. We must take these and check for extraneous roots. Now again, from our graph, we don't think there are any solutions here. That's our guess, but we don't know if we're right till we finish this check. So let's go ahead and check first x equal 11. And remember, everywhere in my original problem where I have an x, I would plug in an 11. So my original problem was 2x plus 3 plus root x minus 2. So everywhere I see, I'll plug in an 11. So I have 22 plus 3 here. 11 minus 2 is 9. Root 25 plus root 9. Is this a true statement or not? So root 25 is 5. Root 9 is 3. 5 plus 3 is 8. This does not equal 2. Now notice if this had been a minus sign, it would have been great. And that's one of the things that comes up about extraneous roots, is when you square both sides, that positive and negative difference. So it's important to check it. So here we have to say, therefore, x equal 11 is not a solution. It's an extraneous root. Okay, let's check over here, and remember, same thing holds. Wherever I have that x value, that x, I'm going to go ahead and plug in a 3 this time. So 2 times 3 is 6. 3 minus 2 is 1. 6 plus 3 is 9. Square root of 9 is 3. Square root of 1 is 1. So here we have 3 plus 1 is 4. 4 does not equal 2. Now remember, if this had been a minus sign, it would have worked, but that's what happens with extraneous roots. Therefore, x equals 3 is not a solution either. It's an extraneous root. Now, because neither of these potential solutions are an actual solution, I would have to say overall, therefore, there is no solution. Now, this matches with what my graph said. So that is nice to have your handwork match your graphing as well. Now, we've done some of the toughest problems that you'll see on your homeworks and quizzes. Let's go ahead and look at some other problems where we're still working with roots, but they're not in radical form, they're in exponential form. For instance, we might see a problem like x to the 5 halves equals 32. Now, this does not look like that it's a radical problem, but remember, when we look at this, 5 is the power, 2 is the root. So if you wanted to rewrite this, you could rewrite this as the square root of x to the 5th equals 32. And that doesn't quite look like an exponent. I'm going to try and write that a little bit bigger so you can see that. The square root of x to the 5th equals 32. So let's go ahead and look at this one graphically. Now we can graph this one of two ways. We can graph it with the square root, or we can graph it with the exponent. It doesn't matter. I'm just going to use our exponent, and we'd have to subtract the 32 across and get it set equal to 0. So let's look at x to the 5 halves minus 32 equals 0. So we go into y equal, and make sure we clear that out. Now, if your calculator would use your exponent key and you don't jump up into the exponent, make sure you have this in parentheses, the 5 divided by 2. Subtract the 32 across, and let's go ahead and graph that. Now, we're looking for a solution. It might not pop up. Oop, that looks like a potential solution. But again, there could be more than one here, so we always have to make sure that we look at this and think, okay, this could have come back down and crossed again just outside of the range here. So to get an idea, I want to go ahead and expand my window in the x direction. I want to go, let's say, negative 50 to positive 50. And again, I'm just kind of looking around to see if there's going to be another spot where I cross. Well, that looks like it, but again, it could be over here at 100, but that just kind of gives me an idea. It's looking like it's crossing. So it looks like 1, 2, 3, yep, looks like a potential solution there, but to be sure, my 50 scale was way off. It was way too big. I'm going to scale this back from, let's say, negative 10 to 10 where it was. And again, I was just looking to see if anything else was going on. And I can see a lot clearer here when this works. I have 1, 2, 3, 4 is my solution. And I'll look at the table here in a second too to get an exact solution. Now, if my solution is not an integer, the table won't help. But I can always go to that second calc, look for the 0, do the left and the right endpoint, and that will help me find that solution as well. But I think it looks like an integer value, so let's see what we can find here. I have to scoot way up here to get to 4. And again, this function looks like it's undefined for all of these numbers, and I should get into a spot here right around 0 where I can actually take the square root of 0 to come up with my solutions. Okay, there's our first one, and there's my root at 4 and 0. I might have overclicked though, my solution might just run by, but 4 and 0 are my solutions from the table. So I can see that from the graph and from the table that I have a solution here of x equal 4. Now there might be other ones too, so I have to go and look for them. These are the only ones that I see in my viewing window. So I think that that's my solution, x equal 4. Now thankfully these are shorter problems, easier to do by hand. So this is x to the 5 halves equals 32. Now I want to write this fraction up here in the exponent vertically. So what I want to do is I want to clear that fraction. What I did before is I'd square both sides to get rid of the square root, so I still want to square both sides to get rid of the square root, but now I want to take the 5th root of both sides to clear the power. So you multiply by the reciprocal basically. 5 halves times 2/5. So whatever you do to one side you do to the other. Now I notice here all of these cancel, and on the left hand side I'm left with x equal 32 to the 2/5. Now 2 is our power and 5 is our root. Okay, so I'm going to do this by using my root first because then I have smaller numbers, and then my power. So 32 to the 1/5. What number can I multiply by itself 5 times to get to 32? And the answer is 2, but if you weren't sure of that, you could do that on your calculator. So we can go second quit here to get back to our home screen and go 32 exponent to the 1/5. And I can see that I get a 2 here for my answer. And you could actually take 32 to the power that we're working on over here. You could just take 32 to the 2/5 right now too and get your answer on your calculator. But I just want to show you how these work in steps. So I have 32 to the 1/5 is 2. So this piece is 2 from here. And then of course 2 squared is 4. Now again, if you wanted to double check this, you could go and just do 32 to the 2/5 right away. So let's go back and show you how to do that. Now if you use an exponent and you end up with a caret sign here, you'll want to open parentheses. And here we get our value of 4 too. So that verifies the same thing. So that would have been right up in here, where we did that 32 to the 2/5 is 4. So the graph shows the same thing as our handwork does, and I definitely get a solution here of x equal 4. Let's go ahead and look at one more of these types of problems where I just have an exponent and I'm not looking particularly at a problem in radical notation. It's going to work the same way. Of course I want to start by graphing, and when we start by graphing we have to get it set equal to 0. And let's go ahead and graph this. X minus 2 to the 3 halves minus 125. So let's clear this out first. X minus 2 exponent, and again if you don't have the exponent key, if you just have the caret key, you want to make sure you put parentheses around the 3 halves. And we need to subtract the 125 and graph this. Now this is going to be an interesting graph. When I have that minus 125 in there, it kind of makes me think that a lot of this is going to not be on the screen. So it looks like right now there's no solution because I don't see anything. But I want to change my viewing window, and I really want to expand this because again with that minus 27 value in there, that's kind of telling me that my graph is going to be extreme. So let's look for some roots. Oh, there's one. So it looks like I might have one root. There could be more. There's just one in this viewing window, and I want to figure out where that is. So let's go ahead and zoom in on this right hand side of the graph. So let's go window, x min is 0. Let's do x max of 50. So here's 50 out here, 0 to 50. And there's my graph. It's crossing right in here. That's about halfway. So maybe let's change our viewing window to 30. Let's try this again. So here we are, 0 to 30. Let's see where we cross now. Okay, there we are. So if this is 30, 29, 28, 27. So I think our solution here is 27. And then of course we can look at our table as well to get an idea if that's really 27. You know, maybe I counted backward wrong. So I think that our solution is right there at 27. Let's go ahead and hit the table as well. Now, one problem with the table is, you can see right here, I way overdid it on the table on our last problem. So it makes it hard to get back to a spot where it's easier to find anything. You have to scroll through it. I don't know a faster way to do it. If any of you guys know, let me know. Whoops, I'm going the wrong way. I'm getting higher. I was kind of reading this like a thermometer, where lower temperatures are toward the bottom, but this one goes up. So again, we're trying to get to 27 here. And at 27, I hope that my y value is 0, and that tells me that's the solution. Now as I'm scrolling through these y values, they're positive and they're getting smaller and smaller and smaller, which means they're going toward 0 or negative numbers. So that shows me that I have potential here of getting toward a 0. Oh, there it is. I didn't over click this time. Well, maybe I did. To get my solution. So that tells me that 27 is my solution as well. Not the 22 down in the bottom of the screen, but the 27, which has a 0 across from it. So again, I can see right away here that 27 looks like a good solution. So here's 27, 0. Again, this is the ordered pair, 27, x equal 27, 0. So I think that's my solution. But let's do this problem by hand and see if we can match that up. So problem by hand, x minus 2 to the 3 halves equals 125. So I want the 3 halves to cancel. So I'm going to multiply by the reciprocal of 3 halves, because 3 halves times its reciprocal would cancel and give us 1. So I raise both sides to the 2/3 power. These cancel. I'm left with x minus 2 equals 125 to the 2/3. Okay, so I have, if I add 2 to both sides, I have x equal 2 plus 125 to the 2/3. Now 125 to the 2/3. Let's do 125 to the 1/3 quantity squared. Now 125 to the 1/3, you can do that on your calculator if you want. That's 5. 5 times 5 is 25. 25 times 25 times 5 is 125. So this piece right here is 5. And of course I still need to square it. So I get x equal 2 plus 25, or x equal 27 as my solution. So it matches up with what my graph said as well. So when we're working these problems, again, you just want to think about the steps. Some of them are really, really long, but again, stick to them. Graph them first, because that'll give you an idea. Am I looking for 0, 1, or 2 solutions? Do I have extraneous roots? So these are long problems, but they're definitely doable if you break them down into small steps. And as usual, if you have any questions, please bring them to class, or let me know, stop by my office hours, or shoot me an email. Good luck.